Hello friends and welcome back. In this video we'll be talking about gravitational orbits, so extending and expanding on what we've already talked about with gravity, Newton's law of gravitation and Kepler's laws. So we already talked about circular orbits and elliptical orbits. That was Kepler's first law. And in this video we'll expand on that, extending to the full zoo of solutions that we can find. That describe the motion of two objects. Typically, we take one big, massive object. Let's call it, as usual, some big M, and a smaller object, little m, around it. With around being something of a loose concept, as we're about to find out. Let me move this here and draw the two types of solutions that we already discussed. So circular orbits, and we discovered, for example, that the energy of such an orbit is negative. That's very important, and that it's precisely equal to this value, where r is the radius of the orbit. And obviously then we calculated the orbital period and the orbital speed and so on and so forth. Secondly, we talked about elliptical orbits, where the sun doesn't lie at the center of the ellipse, but at one focus of the ellipse. So something maybe more similar to this in shape, right? Where this is an ellipse and the two foci, one of them is occupied by the sun, and the energy in that case was a very similar expression with the same structure, but with A in the denominator, where A is the semi-major axis. So if we're talking about an ellipse, this is A, okay? So half of the width of the ellipse when we put it sort of on its wider side. All right. So given that in circular orbits the radius of the orbit, it is actually the same as the semi-major axis. It's just that the two things are the same, are one and the same. It really looks like we found some sort of universality in these solutions, in the sense that we can write them together as simply this expression where the energy of whatever solution, at least whatever solution we found so far, is equal to this expression, provided that we give the appropriate name to the semi-major axis. Well, in an absolute shocking turn of events, this thing that I just said doesn't just apply to circular and elliptical orbits, so bound states with a negative total energy, but it also applies to unbound orbits. Let's take a look. Let me move this at the top, and let me move this close to it. And now I will jump ahead a little bit, because proving this explicitly is a bit of hard work and not particularly instructive at this level. But it turns out that if you do the calculations, this very expression holds as the energy for these solutions, even in the following cases of parabolic orbit, with orbit maybe is can be used a little, I'm using a little loosely, namely an orbit where the object moves something like this, where this shape is a parabola. And this is the case where the total energy is 0, which is corresponding to sort of the limit where this semi-major axis goes to infinity. Now, as a goes to infinity, then the geometrical meaning of semi-major axis, in quotation marks, is less transparent and less clear. But at least sort of mathematically, we can replace a equals infinity in that expression. We get total energy equals 0. And after a little bit of, well, more than a little bit of work, you actually get out of it that you can prove that the shape of this trajectory is a parabola, which is absolutely insane. And what else do we need to know about the parabolic motion? Yeah, in this case, the eccentricity. Remember that we had defined this eccentricity as was 1 minus semi-minor axis divided by semi-major axis squared. This goes to 1. Okay. So this is a special case of the equation for an ellipse of eccentricity epsilon sort of becomes degenerate and turns into a parabola, like an open ellipse, if you want, when the eccentricity goes to 1. And last but not least, there's a fourth case of hyperbolic. Maybe let's change color. Let me do it in red. No, 1 IV. Of hyperbolic orbit or trajectory. And this is when, again, so the total energy is positive now, which is the same as this semi-major axis, again, in some quotation marks, being negative, which, again, geometrically loses a little bit of the intuition that we had built for ellipses, but the fact mathematically I can still express it in the same language, and in that case the eccentricity would actually be bigger than 1, which again doesn't make much sense for the equation of an ellipse, but I can still call it use the same type of formalism. And in that case I don't have enough drawing skills to be able to tell the difference to draw the difference between a parabola and a hyperbola, but something like this maybe. That's my best attempt. Don't quote me visually on this. All right. So let's try to summarize. Let's get to a new page and let's summarize what we found. So, what I just told you. So under the big umbrella of solutions to the orbits of two gravitating bodies that all have this form, we found two types of bound states, namely systems with negative, let me write it a little better, negative energy, which were circular and elliptical, and two types of unbound states, which, for objects of astronomical interest belong, for example, to comets or with respect to Earth or, other asteroids and bodies like that, where, not all comets, by the way, but some, where the energy is, bigger or equal than 0. And if the energy is exactly 0, then we have a parabola. And if the total energy is positive, we have a hyperbola. Remember that this implied a circular orbit implies that the radius is fixed. So at any point, the distance between the two objects is a fixed number. Elliptical implied that there was that the radius was somewhere between a minimum value and a max value, right? One is what we call the perigee for Earth, or perihelion for the Sun, and the apogee or aphelion for the maximum distance. When it comes to parabolas and hyperbolas, so unbound state, there is a minimum value that for the distance between these two objects, but the max value is not finite, is infinite. So conservation of energy and angular momentum don't allow the distance typically to get to zero, except in cases where L is equal to zero, angular momentum is equal to zero as well. But the more generic statement that I wanted to get to was that there's no maximum distance allowed between the two objects. That's infinite. In the case of parabolic motion, the speed at which the smaller object reaches infinity is zero. So I do get to infinity, but slowing down all the way to zero at the very end. And for the hyperbolic motion, where the total energy is not only zero but bigger than zero, actually there's a finite speed. So I get to infinity and I have some kinetic energy to spare. So that's the key difference between parabolic and hyperbolic motion in this energetic context. Speaking of energy, I hope you remember, or I hope you'll go and check again, the video on central potential, central forces, and effective potential. And we learned that there exists this very useful tool of the effective potential that really helps us capture the physics and the behavior of the system in a clever way. And we discovered that it was equal to this combination. So there was this repulsive term, L squared divided by 2mr squared. And then in the case of gravity, there was the usual expression for the gravitational potential energy. And we plotted the graph of this function, and we found that this graph is something like this. Let me plot this a little thicker, maybe like so. That is something like this. Wonderful. Where this is the distance between the two objects, and there's sort of energy or potential energy on the y-axis. Okay. Now, a very nice way to display the various solutions that we talked about now is to look at what points or what areas or what properties they would have in a graph like this one. So to start with circular orbits, that is the orbit that has as value of energy, of total energy, precisely the one corresponding to the bottom of the effective potential. And so energy conservation guarantees that there's only one allowed value of r, which is precisely the radius of the circular orbit. So this is circular. So in a sort of potential energy graph like this, the existence and the properties of a circular orbit are immediately captured by saying, well, it's that value where the energy is precisely here at the bottom. There's nowhere else to go. And so the allowed ranges of r are between r and r, the radius and the radius. So there's nowhere to escape. The second solution we talked about is elliptical. And by the way, notice that as we said, the energy is negative for the circular orbit. And elliptical orbits have a value of total energy that is still negative, but higher than where the bottom of the effective potential lies. And so you see that the allowed range of radii, of distances that I have in this situation, is somewhere between a minimum and a max value, right? And if I am, for example, if I'm at a different location, let's say that I am here, well, the amount of kinetic energy that I have available is precisely this quantity here. Actually, I said something a little silly. It's not precisely the kinetic energy there, but it is the value of 1/2 m r dot squared. Because this extra term in the effective potential actually came from writing the kinetic energy in polar coordinates. But yeah, if you forgive this blunder from me, everything else that I said is actually correct. So elliptical solutions have a negative value for energy and a value for energy as a result, the values for the distances are somewhere between a minimum and a maximum value. I expect you can see where this is going, because then parabolic trajectories where the total energy is 0 lie here. And we can see that there is indeed a minimum value of the radius allowed by energy and angular momentum conservation, but there's no maximum value, no finite maximum value. The maximum value for the distance is infinite. And so again, that's the first solution when the energy is exactly 0, where I have an infinite maximum distance allowed. And the energy equals 0, we were able to conclude as a result that the speed at which I would hypothetically reach infinity is also 0. And finally, hyperbolic solutions are the ones where the total energy is positive, somewhere here. Again, there's still a minimum value of the radius, the distance between the two objects. Again, there is no max value, and I would actually reach that R max equals infinity with extra speed to spare, with some kinetic energy left over. So yeah, very nice, very, very, very interesting. Finally, and this is one of the probably the most useful things from this video when it comes to solving exercises and interpreting your results. I want to tell you and give you the vis-viva equation, which is the following. Let's write it down. Vis-viva equation. Okay. You may remember actually these two words, vis-viva, from introphysics, because that was the live force, the old name for kinetic energy. And it comes precisely from a way to look at energy conservation. So we said that all of these solutions have this general expression for the total energy, which is minus G, product of the two masses, and then divided by 2A, with A taking a geometrical role that is not that is a bit non-trivial, but still this remained. And we also know that the total energy is, 1/2 mv squared plus the gravitational potential energy, namely 1/2 mv squared minus G, product of the two masses, divided by R, where R is the distance between the two objects. Now we can solve this for, and so this was equal to 2gm divided by 2a. If you solve this for v, well, the m's conveniently cancel out, the 2's do their thing, and what you find is this equation where v squared is equal to 2 over r minus 1 over a times gm. And this, my friends, is precisely what historically people have been calling the vis-viva equation. And so at any point in this orbit, take an orbit with a certain value of the semi-major axis A, all right? Again, this could be either equal to r for circular orbits, positive for elliptical. I don't know why this did this. It could be infinity for parabolic, and it's negative for hyperbolic orbits. R is the distance between the two bodies. Okay, so as usual, when I look at these two objects, this is R, and A is a geometrical construct. And this, at all points, gives you the expression to calculate the speed of such an object. All right, so, or vice versa, if you have the speed, it allows you to calculate whatever other unknown you have. Very, very useful and very, very interesting. We'll definitely utilize it in the tutorials, especially tutorial B, I think. But yeah, this was it for Kepler and gravitation and Newton's discovery of the universal law and all of its, or some of its consequences. So I look forward to working with you, and thank you so much for watching, and see you soon.